This is problem 2 on practice exam 7 of chapter 2 in the book Problem Solving with Differential and Integral Calculus. We have an airplane flying at 30,000 feet and has to make an emergency descent to 25,000 feet over only 50 seconds. So the path of the smoothest transition, which is a great calculus problem to figure out, it's given to you right here, is this. So part A asks for the rate of change of the altitude with time, dA dt at 25 seconds, and part B asks us to take the derivative to get the slope and compare it with our answer in part A. So part A, we need the slope. So we're going to locate the point. There it is. We're going to add in a good tangent line. Right there, the rise is minus the whole thing, which is minus 7,000 feet. The run, that's 2, 4, 6, 8, 10. That's about 2 seconds to about 49 seconds. So that's a run of 47 seconds. So the slope is minus 7,000 divided by 47 seconds, which is about minus 149. I probably should round that to 150, but I don't like to round things. So now part B, we're going to take the derivative. So for t in the normal equation, we're going to plug in t plus dt, and as a result, the altitude is going to change by dA. So we're going to start by cubing that, squaring that. It's going to be big. 2 lines. A plus dA is this whole thing. And the first thing we can do to make it shorter is to get rid of the dt squared, which is right here, and there's a dt cubed. Those are all 0 compared with dt. They're infinitely smaller than dt. We can throw them out. So that leaves this. Now we can subtract a from both sides. A is 0.08 feet per cubic second times t cubed, which is right here, minus 6 feet per second squared t squared, which is right here, plus 30,000. So the 30,000 is going to go away, and we're left with that. That's the derivative. That's dA. That's an equation for dA. And if you know the rules for taking a derivative, you're not surprised. So now we can get the slope. We divide both sides by dt. Now we have dA dt, and we want the slope at 25 seconds. So we plug in 25 seconds for t. This equation, dA dt, is good for all time, any t you want. If you plug in 0, you're going to get a slope of 0. And if you plug in 50 seconds, you're going to get a slope of 0 because the plane is flying level here and level at the end of 50 seconds. But here we want 25 seconds. So we put that in, and we punch the numbers in the calculator, and we get minus 150 feet per second. And if you remember, we got minus 149 with our tangent line, and now I'm regretting not rounding it to 150. Anyway, they agree. That's problem 2.